This is everyone? Yes.
Yeah.
Nice.
I guess I'm gonna do an intro. Thanks everybody for coming. This is sort of like a last minute talking like, but I'm very excited for the pod. This is Raj. He is a postdoc researcher in the Mosaic team in AI tool at the Institute of AI. He received his PhD in Georgia Tech. We're from the School of Interactive Computing, and the professor was Mark
Riddell.
Mark Riddell. And I guess the lab works on entertainment and intelligence, and the AI tool, he works on, I guess, a range of stuff on NLP, on embodied AI. And I guess the talk today will be more about war models, which could be interesting to lots of people in these labs. And yeah, welcome, Raj. Thanks for giving the talk last minute, right from Europe. And I'm excited to hear about this.
Sounds good. All right. Thank you guys for having me over. So today we're going to talk a little bit about modeling worlds in text. So before we sort of get like any deeper into things, I want us to sort of zoom out a little bit and try to take a big look at the picture of this, right? So let's think about how people use language. People use language to interact and affect change in a dynamic world around us. And why is it that despite all the advances in the past few years, right, you can go on Twitter today and like half your feed will just be ChatGPT screenshots, right? So despite all of this, agents that can sort of communicate with people and each other, at least in a manner that is contextually relevant, is rather primitive, right? Like, why is it that people don't actually use things like Alexa, Cortana, or whatever? And I'm going to posit that this is partially because you can't plan with them, right? They don't learn from feedback. They don't really say things that make use of general world knowledge. And what is needed to actually get these agents to do the things that humans do so easily? So to answer that, we need to first identify some critical components of learning that are missing from these kinds of deployed, language technologies and systems. So this is partially part of the problem, right? Scale is quite impressive, but there's only really so far you can go by feeding the monster, right? So just sort of throwing things at a GPT, the entire internet, is not going to teach them, how to act or speak based on the context around them, because they were never really trained this way, right? So the two sort of key components that I'm going to posit are necessary for training these kinds of models is first interactivity. It's a term I mentioned earlier. And it's this idea that we teach and, we learn interactively. What we say or do is refined in a trial and error loop in this sort of tight feedback loop. And at this point, even within pop culture, one of the ways that we can tell that like an AI has sort of human level intelligence is how they display their intelligence. So this is a screenshot from some episode of Mandalorian that I was watching last week. So the second term is situated, right? It's grounding. And at the core, what this really means is the things that we say or do depend on the current context around us and draw from our shared experiences. So you can sort of think of this as intent grounded in shared thought. So this can be anything from a group of people, role-playing characters in an adventure game, something like Dungeons and Dragons, having a common fantasy world that they're all, imagining themselves in, but still extrapolating to real-life experiences, right? Things like camping out in the woods or so on and so forth. And it can be something entirely mundane, as all of us having this shared agreement that, the only real reason that spoons are useful is because they let us eat ice cream. Right? It's this idea behind common sense. Okay, so, this sort of idea of training these kinds of like situated interactive language agents seems really interesting. So why haven't people done this, right? And the simple answer is that building sort of realistic simulations for these kinds of agents is really quite hard, right? So this is equivalent to, I guess, building what some companies will call the metaverse. And no matter what you hear from PR pitches, this is not happening anytime soon. So this is, so as a bit of a history, I used to be a game developer at some point. And so this is like a really favorite example of mine that was on Twitter a couple of weeks ago. So there's this Japanese game company that basically made this, and it's, well, It's a bit laggy, but basically what this guy is doing is he's sort of just walking up escalator with the escalator also like moving and his feet are like stepping on top of it. So from like a graphics perspective, this is actually insanely hard. And when this was posted on Twitter, like a few weeks ago, like the entire game dev community like collectively lost their minds. Is like, how do you actually, so if something like this is this complex to simulate, you can sort of think of all the other kinds of like interactions that you would actually need in sort of everyday life. And it's not happening, at least with this kind of simulation anytime soon. So luckily, we're not completely, it's not completely hopeless, right? Creating interactive agents doesn't necessarily require a lot of these physical and or visual components, right? So full embodiment, I will posit, will probably help in the long term, but we got to work within the bounds of what is computationally feasible, right? So we're really looking to try to explore this space of reasoning together, planning together in language, and understanding and learning from feedback. And so which sort of for complexity's sake can be abstracted a little bit, right? So I like to think of this as sort of a complexity trade-off. In return for having simulations where you don't have motor control and visual perception, you get sort of more complex cognitive tasks, things like making a recipe together, going out into a world, adventuring on a treasure hunt, having complex dialogue conversations with other agents. So the question now is there sort of a more tractable platform on which we can sort of easily and cheaply simulate language communication grounded in real world actions? So this is the bit where I ask how many people in this room have actually heard of text games or interactive language games before? And oh, here you go. That's one more than usual. Two more than usual. Fantastic. So this is a genre of games that basically you can sort of think of it as video games, except everything is in textual natural language. So take this for example. So when you agent first enters a world, they receive a description like what they see on the screen here. So, in this particular world, the agent's job is to try to perform scientific experiments to determine something. So in this case, you're trying to determine if an aluminum foil is electrically conductive. And then it gives you like little bits of information of what you see in the world around you. And you can also type in actions using textual natural language for what you actually want to do. In this particular case. So you type in, you sort of look around and you get this natural language description of what the world looks like, So in this case, you're basically trying to find some aluminum foil, like make a circuit that puts the foil together to try and find if it's actually conductive. So, you go around, walk around this house, navigate around, pick up the aluminum foil, and then, you see, okay, so what is the actual scientific experiment that you need in order to determine whether this aluminum foil is conductive? Well, you got to make a circuit out of it, right? And so you see a bunch of the different kinds of components for this circuit over here. So there's, a bunch of light bulbs and wires and so on and so forth. And you can sort of see, like right here, you see this light bulb is off. And so I'm going to mostly like skim through the details, but basically, the agent is sort of like, moving anode to cathode to anode, like actually like putting this circuit together. And once it like puts the circuit together, the light bulb, which was off, is now on. And so, you've basically made a circuit with one of the components being this material that you were testing. The light bulb turns on. That's sort of a way of knowing that this material that you have is conductive. And, that's how you complete the task. And so the actual way of, finishing this is sort of entirely left up to the agent, right? The agent only receives this instruction as like, you're given this kind of material, go find out if it's conductive or not. And then you sort of have to basically come up with your own experiment on how to do it. So this is sort of a nice pixel art-y version of what's actually going on. And so, there's a bunch of different rooms and like locations and whatnot within this kind of world. And the agent sort of like goes through, explores, tries to find and collect all the materials that it needs to perform this experiment. So, that's not the extent of it. So these games can get sort of like very large and complex very quickly. They've existed since the early 70s. And so when people have been building engines, the sort of simulation engines out for the better part of the last like 40 years, these simulations can get pretty complex. This is actually one of the earliest like text games, Zork. So every single room that I was showing you around is equivalent to like one of these. And so games like this have a few hundred to thousands of locations, characters, objects, all of these kinds of things that agents need to keep track of while they're trying to actually go out and fulfill their objectives. Okay, so I told you guys sort of, like at a high level what these kinds of environments are. So more mathematically defined, text games are POMDPs, partially observable Markup decision processes. And so they consist of this sort of like 7-tuple of what you have see on the screen here. And so at every step, the agent gets the observation, the textual description of what the world looks like. They can pick an action, which is basically sequentially decoding in natural language, the exact action that they want to do. And then, the action is executed within this engine. The world changes somehow, and then the agent gets another natural language observation as well as some kind of a reward, which is giving it an indication of whether it's making progress towards its goal or not.
So the agent actually outputs the text, and somehow the engine parses the text.
The engine parses the text. Yes.
How does it decide like dynamics or the causal sequence?
It's baked into the engine basically. So it's like if you have a get item, right? So the get basically is like a subroutine within the engine, which is I want to pick up this. And so if I say get roll of tissue paper, it'll basically transfer the roll of tissue paper from its location on the table to now the location within my inventory.
And your actions are natural?
Yes. So you can sort of think of it. It's natural language, except not everything that you output in natural language can be parsed by the engine. So there's a subset of things that can actually be like executed within the environment.
Okay, so the agent or the player actually knows that there's no action. That's it.
Yeah, well, it's kind of hard because there's actually still a few hundred. There's a few million still possible kinds of like actions that they can sort of type in. But generally, like if you type in, some of these games have things like help hints. So if you like type in help, like it'll be like, okay, here's some of the kinds of actions that you can try to do. It's sort of like, when you are doing Alexa, it'll be like, try saying this, that sort of thing. Yeah, I'll get more into details about what the sort of exact action spaces and stuff look like. So there's really 3 primary challenges for why these environments are actually so difficult, right? And I'm going to get a little bit in depth into each of these. So the first is, well, both state space and action space are all natural language here, right? And so a bunch of these games require these kinds of actions and dialogue to complete. And so, assume, like you were saying, so even if there was only 1,000 possible like things in your like natural language vocabulary, each action is about 5 words long, let's say. That's still 1,000 to the power 5 possible things that you can sort of type in at every single step. And some games actually require more like natural conversational dialogue with other characters and stuff to finish, which is a little bit more free form. And as a consequence of everything being in natural language, the sort of state action space is, again, it's distributed via the sort of like Zipfian law, where the most important actions and states are seen very rarely. So if you basically just take and like group all of the words and tokens that you see, and spread them out in the sort of like histogram that you're seeing here, you're going to see some words that are like seen very often, and other words and entities that are seen like only 1 or 2 times, but that also like end up becoming really important for how you actually finish these. So, one question here is, how do you actually make RL algorithms that can handle these kinds of environments? So, traditionally, a lot of popular RL algorithms, PPO, TD3, all these kinds of things, they're either meant for continuous or relatively small discrete action spaces. So how can you adapt them to the sort of like large combinatorially sized spaces? And then there's the question of partial observability. So remember, I was telling you earlier, there's, thousands of locations and characters and so on. So how do agents actually maintain a state of like what's happening in this world, right? The observation that you're given at every step only gives you a potentially incomplete description of what's sort of like right in front of you. And so you have to maintain track of everything else. And so one way I like thinking of this is thinking of it as a textual slam problem, where the agent is trying to learn a mental map of the world as it's going around and exploring and figuring out where things are. And then the third sort of primary issue here is that of common sense reasoning. So because everything is in natural language, we're sort of able to ask this question of, how can agents interact, intelligently interact with common objects and things that they see in this world? So think about what it would take for one of you to actually go out and play these kinds of games, right? So you come baked in with a lot of priors, things like knives are, items that can be used to cut things. Spoons are things that can be used to eat ice cream, right? So the question is like, how can you give agents these kinds of priors to bias their action spaces so that, they perform one action, more likely than another? So, before we go any further, there's a bunch of these kinds of problems that I said. So I wanted to make sure that, GPT-3 doesn't just already all solve them. And so, I threw one of these kinds of questions in front of GPT-3, right? The example that I was showing earlier. So is a metal fork conductive, right? Okay, so GPT-3 says, yes, a metal fork is absolutely conductive. And so, trying to like guide it a little bit. So how could you use a battery and a light bulb to test if a metal fork is conductive? So if you remember the example that we saw earlier, this is exactly the kind of experiment that the agent was trying to do to determine if this item is conductive or not. So, it gives you something like vaguely plausible, right? The battery light bulb can be used to test, you just got to take the battery, take your fork and just stick it to both ends of the battery, which sounds fantastic, but you would short a circuit, if you actually did it, right? And so this is kind of the problem with large language models at this point. So they contain sort of vaguely useful knowledge, or vaguely useful seeming knowledge, at least, but none of these are grounded within the actual dynamics of an environment. And so when it comes to actually executing these kinds of instructions, you can't. So it's sort of much more high level. And so that brings us to the sort of key hypothesis of what we're going to talk about today. So I'm going to hypothesize that, agents with internal world models are going to be able to produce language needed for interaction more accurately. And so, I said the magic word that was in the title. I said world model. And what is that, right? So that's where we're gonna sort of start today. I'm gonna talk a little bit first about actually making the world model using knowledge graphs. And then we're gonna spend some time actually taking that world model out for a spin in this world and actually using the world model to train reinforcement learning agents. And then depending on how much time we have at the end, I'll give you a bit of a brief view on what my current work is in bringing it to visual domains, visual, more control types of domains. Okay, so the first bit, how do you actually make a world model in text? So remember, I gave you this POMDP definition a little bit ago. And so out of all of the things within this POMDP, state space, action space, whatnot, the thing that we're most interested in is this transition probability matrix T. So this transition probability matrix T is what dictates, sort of given an action and a current state, how is the world going to change to the next state? And so, this is this idea, you have this matrix that ends up being something of the order of, twice the size of your state space times your action space. And, you're effectively, to learn a useful world model, you would basically need to learn some kind of an approximation of this transition matrix. Yeah.
Okay, so the game engine itself is basically, so can be considered as like a form of world model, right?
Yes, it is.
Representation of that.
Yes, so the game engine, so the idea is the game engines for most of these were built up over the course of 20-something years, and they're usually a couple million lines of code. So that's a little bit hard. So what we're trying to do is we're basically trying to see if we can learn representations, basically the game engine, by interacting with it.
And more complex.
Yeah, a more concise version, effectively, hopefully one that doesn't take 20 years and multiple millions of lines of code to write out. So this is sort of like a back of the envelope calculation for what the engine actually sort of like what the size of the transition matrix looks like, right? So for the sort of input space of natural language vocabulary, it's about 50,000, which is the standard sort of GPT-esque size vocabulary. And so, you have about 512 tokens across 50,000 possible things that you can pick from every single one of these tokens. And then your action space, let's just say it's like much smaller, 1,000 possible tokens, 5 words. That still gives you this like unholy number as like the naive lower bound on the dimension of what this transition matrix looks like. So I kind of threw a lot of problems at you all. And this actually seems like a really hard problem to try and learn a concise representation that doesn't take multiple millions of lines of code. And so this is one solution, right? So knowledge graphs, right? So the key to this solution is that we're going to get agents to represent the state of the world in the form of a knowledge graph. So these knowledge graphs are sort of like a very intuitive ways of representing these kinds of worlds. They're easy to understand. They give us structured memory aids that help with the sort of partial observability that I talked about. They contain information about common sense reasoning, the world that you sort of like move through. And people have been using graphs as guides for these sorts of very large action spaces for quite some time now. This is actually a hand-drawn map for the example that I was showing you guys earlier that I did. And so what does this graph actually look like, right? So formally, this graph is a set of triples of subject, relation, object that's sort of built up as the agent explores the world. And what the agent does is it takes the sort of textual description and then it somehow extracts a representation out of this textual description that gives you information on things like locations that you've seen, objects that you've seen, attributes for different kinds of objects, and so on. I'm going to get more into detail about like how the actual representation learning for this goes. That's the sort of the core world modeling approach. And so the intuition is that, knowledge graphs are a lower dimensional representation of this sort of higher dimensional transition matrix space of natural language. And so because they're smaller, the rank of this sort of matrix is lower, and it's hopefully going to be much easier for us to learn. So what does this look like, right? So let's take a look at just example of one single transition. Yeah.
Sorry, how do you decide like what's the right level of generality to keep your graph? Like I could imagine like for specific tasks, like downstream tasks, like this would be to a course level, or like how does that trade off get?
Yeah, that's a really good question. So I think how coarse or fine-grained the graph should be kind of, again, like one depends on your sort of like end goal task. But the kind of graph that we have here, I think, is fairly general in that like it works for these kinds of problems. But the exact same representation in our current work also works for domains like Minecraft and Thor. So this is what the graph actually looks like. So on the left hand, so you see the sort of textual description of what the agent sees, right? And you have what the knowledge graph is. So you are the agent. You're in this location that's west of a house. The location has a mailbox and a house, and the mailbox has like some kind of attribute, like if the mailbox is openable. And then you perform this action. You're going from west of the house, and then you perform this action of north. And then the world transition, like the world changes. You're now in a different location. You now get this, you're north of a house instead of west of a house. And so the whole job for this kind of world model is basically given everything on this sort of left side plus this action. You want to try and predict what the right side is. Basically, your state plus one as a function of your previous state and action. So what we did was we went and basically collected a bunch of these from a variety of games and different kinds of like tasks. So this is something like 30 years worth of like text games. And it like basically results in a data set, an offline RL data set you can think of, that consists of 7,000 different kinds of entities within these graphs, multiple different 17 unique relations, and of all these kinds of transitions. So if you actually kind of look at this, like this is actually a bit of a hard problem, right? This is literally just the first two steps. Like the agent drops into the world here and it makes one transition, and already like it has this much information to sort of like think about. So imagine what happens when it's actually like finished exploring, like what does the size of that graph look like, right? So actually predicting the entire new graph or the entire new state that the agent wants to see at every new step is a little bit hard, and it's kind of outside of the reach of like most kinds of transformer things today. But luckily, there's a way to short circuit this, and it's by sort of like exploiting the Markov property a little bit. So here's the trick, right? So instead of predicting the entire next state, the way a lot of standard world models do, all you're doing is you're predicting the difference between the current state and the next state. And so the idea here is that if you're predicting the difference between the current state and the next state, it's a much smaller, much more bounded kind of number of facts. So there's only so many new facts that can change about a world given an action that you do within a current state. Yeah.
Question. So where does the valid set of nodes and valid set of edges come from? Is it per game or somehow specify where all of these are features?
Yeah. So it's not per game. It's literally just from the GPT vocabulary.
Okay.
So these are all sort of just like natural language kinds of things that you're like building up from a sort of a natural language vocabulary. So it's like one shared vocabulary across like everything.
So each node is like a vocabulary token.
It's a vocabulary sort of token. That's like basically, so what we did was to make it a little bit easier. So there's multiple versions. You can basically decode these things in just pure natural language. And you can also say, okay, so there are 7,000 entities across all 30 games. And every single step, try to predict what the next node is, right? Yeah. So with that in mind, we designed this model, which is called the world former, that is basically designed to do exactly this, predict what are the actions that you can take in the next step, and also what the world looks like in the next step, given everything you've done previously. So there's a bunch of different moving parts here, and I'm going to go sort of a little bit left to right. So you first start off with a couple of bidirectional, like transformer-based encoders that take the observations, the actions, basically the graph and the current state. So you can sort of pre-train these kinds of things via mass language prediction, graph link prediction on the sort of training set of what you have in the game. And then both of these output a sort of a fixed dimensional vector representation for that particular piece of text. And then you can sort of crunch that down even further using an aggregator that sort of, combines both the text representation and the graph representation. Yeah.
So what will be the architecture of this graph encoder?
Think BERT.
Okay.
BERT architecture, bidirectional architecture.
So
yeah.
you give it a bunch of triplets?
You give it a bunch of triplets just in natural language string form. Yeah. And then you have two autoregressive decoders. So think like GBT that are basically conditioned to take the representations that you have been learned that have been outputted by these encoders. And their job is to sort of like token by token, like output, what are the kinds of next actions that I can do? And, what does the world state look like at the next step? So the standard, sequence to sequence kind of training in the NLP world looks something like this, right? You have a bunch of input text and you basically offset the text by one token. And you're trying to predict what is the next most likely token based on this kind of like factorization. Well, if you sort of look at like what you're seeing here, you can do a little bit better, right? So actions and graphs are not really just plain sequences. You can think of them as more as sets of sequences. So this is more of a structured prediction problem, wherein you have this structure that, the ordering matters within a graph tuple, right? So you are in this location that's north of the house, is like an ordering that actually matters, but outside of this, the ordering doesn't matter whatsoever. And so using this kind of intuition, we can basically have this sort of set of sequences formulation where instead of trying to decode one token at a time, we're basically trying to decode sets of these kinds of things that you see here one at a time. So one single tuple or one single action all at a time. And that gives us a new sort of a factorization. Instead of doing just autoregressive like left to right, we can get a new factorization where we're doing, one set of things one at a time in this sort of like permutation invariant way. And so I'm going to skip through most of the derivations of this, but what like you end up getting is you end up getting two new sort of like losses, one for each of these autoregressive decoders that can just sort of then be added together in this set of sequences fashion to train this whole thing end to end. Yeah.
Question. You mentioned that we're predicting like the difference between two graphs.
Mhm.
And you also mentioned the graph is represented as a bunch of triplets.
Yeah.
So what is the representation of this difference between them?
The difference is also just triplets. So if you're thinking, right, so one's a set, the other's a set, it's just set difference. And so the set difference is also like triplets.
Interesting. Okay.
Yeah.
I have a question. How do you decide the size of the set of sequences?
Combinatorial in your vocabulary.
It's combinatorial, but it's permutation invariant within your vocabulary. That's the sort of whole point of this.
I see.
Yeah. So we tested this on a bunch of different test tasks, sort of zero shot that it's never seen before. And so what you're looking at is like each one of these columns is a different kind of zero shot game that it's never seen before. And each one of the rows is a different like model. So starting out from just like a rules-based approach for like extracting and trying to predict a knowledge graph to, question answering, standard sequence to sequence, like what the previous current like state of the art world model was, so on and so forth. And I'm not going to make you read those numbers. So I made, nice, like two nice bar graphs to look at. And so the sort of gist of what's going on here is that the world model based approaches, heavily outperform all previous approaches on sort of, not just the graph extraction, but also in terms of predicting what are the kinds of actions that you can take at the next step. So it's also worth noting that the sort of like first rules-based approach was actually also by me. It was like Delta, it was at the start of my PhD. I don't know how long ago now. And since then to now, like we've had a lot of progress. So at this point, like world models are actually getting to be to the stage where they're actually useful for an agent to actually try and base their actions on. And that's what we're going to look at now, right? So we now have the ability to predict sort of a knowledge graph of the next state given a text description, right? So how do you then use this to enable an interactive agent to more effectively explore a world via reinforcement learning?
Sorry,
Yeah.
another question. So the data set you have shown before,
Mhm.
like what is the form that does the graph contain in a data set?
Yeah. So you can basically extract like knowledge graphs. A good chunk of it was human annotated. And it took a long time. But basically the idea is like you have this sort of like text descriptions paired with graph, paired with actions to the next transition in the sort of like offline, think like offline RL data set.
And then
Yeah.
the result we see before is how accurately can it predict the transition dynamics?
Yes, exactly. And also the actions that you can sort of take, which is basically part of the dynamics. Yeah. So now that we have the ability to actually do this transition matrix, the task is to now find a policy, which is basically just this mapping from state space to action space that maximizes expected rewards within this environment. So I'm going to drop straight into this in the sort of interest of time. So at every single step, like I said, the agent gets the sort of like text observation from what they see. This text observation goes into this world model, which basically like, gets you this graph to predict this graph. And then the graph is updated at every single step. So remember we were predicting the graph difference, right? The world model. And so what you can do is you can basically take your current graph, and if your world model predicts the graph difference, you can just merge your graph difference from what the world model predicts into your current state to get you the next state. representation. And then this graph then sort of gets crunched down. This graph still is in symbolic form, right? It then gets crunched down into this sort of d-dimensional vector representation using a graph neural network. And this basically is just a graph attention network that takes the information in the graph and sort of aggregates it by prioritizing sort of, which are the most relevant parts of the graph should I be attending to in this particular state so as to actually maximize rewards. Yeah.
Does this also allow you to handle like errors in the graph? So if you have errors in your history because you're including it down again, could it like theoretically deal with these?
Yeah, so if you have errors just in the, so there's two possible sources of errors, right? So your world model could have made an error. And then what this does is this is basically conditioned on the error that like your world model like has made. And so the idea is like, hopefully, like, through this process, eventually like end to end, because at the end of this, like what you're learning from is basically a policy gradient for the rewards. And so if it turns out that like, there's one or more parts making mistakes, like you probably will not get as high a reward as you could have otherwise. And so, making those kinds of mistakes will then be penalized. Yeah. So yeah, you have these kinds of encoders, and then you have this sort of like action decoder that sort of takes in all of these and conditioned on this, basically, outputs what you're actually supposed to be doing. So, in this particular case, you can select a template, which is, one of a few 100,000 like action types that you can do, and then fill those in, right? So, take a lantern from a case. So on and so forth. And so the key use, one more use of the knowledge graph here is that we can use it to constrain the exact kinds of like templates and actions that you can do, right? Because not all of these objects and things in your vocabulary will be relevant at a given particular thing. So you're not really going to try to be interacting with objects that you've never seen within the world before. You're not going to be trying to do actions that you've never really, seen or you don't really know the sort of conditions of. So I'm going to mostly skip through the actual details of how this is trained, but you can sort of think of this as it's trained actor-critic fashion. So, given the state representation, the state representation goes to this actor. The actor then tries to basically like decode step by step as a sequence of like multiple different kinds of policies. And then you receive a reward from it. And then you're sort of just doing A2C training on top of the reward from there.
For most, sorry.
Yeah.
So for most of the environments, usually what is the reward? Is it like within we have a task or like the score or something?
Yeah. So the reward is basically what the like it's usually very sparse. It's just like a 0 or 1 in most cases, like at the very, so like in the case of the science example that you saw earlier, basically like if you correctly identify that the aluminum was conductive, you get a +1, and that's your reward at the very end of the game. And so they're very sparse rewards, basically. You usually get them at the end of a couple hundred steps. Yes, you do. You absolutely do. And so let's first just look at like, how well this world model like works. So having this sort of world model, improves sample efficiency a little bit. In terms of what so the top one that you see here has the knowledge graphs, and the bottom was A2C agent that doesn't have the knowledge graph. Is literally just a transformer encoded state representation. And so this is, you're basically looking at like reward versus like, how many steps of interaction it has with an environment. And so, they improve sample efficiency, but, asymptotic performance sort of still stays the same kind of. And this is what you were saying. You still have very much an exploration problem where it's really hard to actually go through and explore every single possible thing within this world. And so how do you fix that, right? And I'm going to go I'm not actually sure how much time we have left, but somewhat in depth about this. And to understand why this happens, we need to take a little bit of a closer look at the structure of the tasks that the actual agent has to perform, right, in the world itself. So there's a critical difference here. So this is a map of the world of Zork, right? It's actually a more complex version of the science example. And so every single one of these things is, you can think of it as like a blueprint for the game, is a different location. And where these things are places. So the objective of this particular game is to collect treasures. And so every single one of these places, you collect a treasure, you get a bit of a reward, but also like there's a lot of different locations. There's a lot of different kinds of objects. And so how do you actually narrow down like, and, give the agent priors on how to explore certain sections of this world more than others, so that this problem of like actually exploring things is viable? And so I was thinking really hard about this, and I was thinking about how I played this game. So when I first played this game was in high school, and it took me about 2.5 months to finish, and figure out and like go through and like explore and put everything. But what I ended up doing was basically I made a dependency graph for the kinds of things that you needed to do in order to progress within the game, right? So this dependency graph is basically the sort of set of dependencies that the agent needs to finish in order to move to the next sort of step in the game. So, an example of that is when you first start out, you're in this like particular location, you've got nothing in your inventory. And to get some of the rewards, you need to make it up to this other location. So up a tree, and that basically will give you what this golden, and pick up the golden egg, which is a treasure, which will give you some amount of like rewards, right? And so, when you have this kind of implicit, like, directed acyclic graph, that's sort of underlying like all of these tasks, what the intuition here is that there's sort of bottlenecks in this state space that you need to get through in order to actually progress to the next section of the game. And so the way we're going to do this, and I'm going to skip through like most of the details of the actual like mathematical definition of the bottleneck states and all the proofs and all of that. Happy to send you guys the papers afterwards to read. But the intuition really here is that what's happening is you're basically going through a world and trying to learn a knowledge graph, right? So like basically through the world model. And what this knowledge graph is doing is you're basically building up a knowledge graph of all the facts that you see within the world. And at any step, if you basically get to a stage where the kinds of knowledge graphs and the facts that you see within the world start becoming stale, right? So the idea is like you aren't really learning any new facts about the world. That is generally an indication that you're kind of stuck. Basically, you're not seeing enough rewards to really progress within these tasks, which also means that if there's a particular section of location within this world that you're starting to sort of see less facts on than before, then that is potentially an area of the world that you want to try and explore a little bit more. So, yeah.
Is that correct for me to understand? It's very similar to the curiosity-driven exploration.
Yes.
That you
Yes.
use your like prediction error or like graph, whether it's
The graph error. Yes.
To decide whether it's correct.
Yes, that's exactly it. So it's basically intrinsic motivation for the agent to learn as much information about the world as possible. And so it turns out that this kind of like, information seeking objective for the agent is actually really quite useful in improving exploration in these kinds of worlds and figuring out exactly which sections of the world to prioritize exploration in. And so, this is like just an example of, an agent, like how an agent would normally explore, right? Just like standard like A2C exploration, it'd basically be wandering through all of these kinds of rooms, trying to like pick up objects, put down objects, try to complete its task until it gets to a point where it is stuck, right? And so when this intrinsic motivation like plateaus, right, it stops learning new facts about this world, it can basically go through and pinpoint the sections within its state space where it's basically had, learning less facts within. And then strategically using this sort of like Gaussian. So if I have a particular state where I know that I've learned all the facts about before, you can sort of use this Gaussian to start exploration in a way that says, okay, I'm going to try to explore more closely around the states that I've been stuck at before, right? So basically the states that I think I've learned everything about, I'm actually going to try restarting my exploration from there and trying to go on in this world.
Is this Gaussian an analogy or an actual Gaussian?
This is an actual like Gaussian. So basically you can sort of say, so if there's a singular state where, you've decided, okay, I'm going to start like backtracking and exploring in, you can figure out what are all the adjacent states to that particular state, right? And so that's the original state is the one that you would want to try and restart exploration with highest probability. And the adjacent states are a little bit less, and then so on. So it's basically, this is sort of like the sort of Gaussian heat map on where the agent starts restarting exploration as it's going through this world. Yeah, so I think I'm slightly running over time, so I'm gonna skip through most of it to get to the results. And basically the idea is like, once you sort of add in this kind of intrinsic motivation and this sort of like additional like planning aspect of being able to like backtrack through and like selectively explore different kinds of branches, that again, like it significantly like improves the actual asymptotic score that you see. So we get through the bottlenecks that we were showing you earlier. And this is not just across this like singular game. We tried it on like a bunch of different games. So this is basically the intrinsic motivation based agents. These are all the sort of like previous state-of-the-art kinds of agents. Yeah.
Yeah, I cannot stop thinking like in your previous slide, did you try to run it for longer?
Yes. We did try to run this for longer. So this, what you're seeing is like the intrinsically motivated agent actually keeps going up,
Okay.
but then the other ones like stay.
Just, okay.
They flatten out at that line.
Okay. It's probably nice to like just get-
Yeah, and I was kind of just like, yeah, we decided to cut it off because like it would seem a little bit unfair because as you start going, this keeps going up, and so for like visualization's sake, we just cut it off here. But yeah, and so, actually like very recently, we did all these kinds of experiments. Like some of you might be familiar with things like decision transformer and this idea of like reward condition supervised learning. And it turns out that like this knowledge graph based world model with like very small number of parameters, right? Like 5 million like transformer parameters is very steadily like beating out transformer-based models that are 10, 20 billion kinds of parameter sizes within these environments. And so what should you take away from that, right? So you should take away that, world models as knowledge graphs significantly improve sample efficiency for interaction in these kinds of environments. Better world models lead to better sort of bottleneck detection through this intrinsic motivation and improves exploration selectively. And basically, okay, yeah. So detecting bottlenecks lets us backtrack and like search through only the most important parts of the kinds of search space. So very briefly, like some of the future things using this base idea of world models, it turns out that there's a lot of different kinds of things that you can do. So one is this idea of like value alignment, where you're instead of like learning just how to finish a task, can you learn how to finish a task in a way that doesn't harm other entities in the world? So basically, safe constraint like reinforcement learning. And it turns out you can basically, bake prior knowledge into your world model that gives, agents sort of priors and, biases them away from doing actions that harm other entities. And then you can use the exact same idea for basically, once you've learned a generative world model, you can use it to generate multiple different kinds of worlds as curricula for agents to train in, and then you can use those to train dialogue agents, basically, purely dialogue with some amount of like action grounding. Yeah, and then this is actually a paper I just presented at like NeurIPS last week. And so having the world model also lets these agents be explainable, because what they can do is they can point to the facts within their knowledge graph that are most influencing their choice of current action. And they can say, these are the facts that I had that are like influencing this action. This is why I'm doing what I'm doing. And it turns out that, when you run human user studies, that like significantly increases like trust in these sorts of agents. Yeah. Thank you. That's all. You can find, yeah. Yes.
Yeah, so like, again, I really like how you presented the talk. It looks like this is like a one PhD worth of research. And then like, I like how you make it like a very concise story and I can just understand it. I have a question about, so it looks like for this world model, this graph is need to be part of the data set. So how, and then somehow require some kind of human element. How can we scale this to the level of, let's say, GPT of like?
Yeah, that's a fantastic question. So basically, how I would say you would scale this is, instead of directly having a human annotate what the graph looks like, we've now at the stage where you can ask a GPT or something to give you what the graph looks like, and then have a human fix. Right. So instead of having the human be the generator, you can sort of use a human as a filter, which ends up being a much more scalable problem, and is kind of how like all of the reinforcement learning from human feedback kinds of stuff does. So it's like, the GPT or something generates multiple possible versions of the graph, and you can sort of be like, okay, which one of these best maps to what the actual like world looks like, and you can generate this sort of human in the loop kind of data set generation techniques that we're trying out.
Given that it looks like this graph is just it's a dimensionality reduction of the entire transition matrix. Is there any way we can learn just generatively from the data itself and then compress it into this graph?
Yeah, that's a good question. So that's actually one of the earliest things I did, is basically just remove this graph completely, and just try to like predict different kinds of things, right? Just only entities within the world, or just like the entire like natural language text. It seems that this sort of graph representation is the right balance between expressivity and also like reducing dimensionality. It's potentially possible to learn like directly from it, though I'm not actually sure what that representation would look like. And as I said, like one of the other benefits of the graph is that it's explainable, which is not something that you would have if like, you just tried to learn these things. I guess like you could throw it through like an autoencoder sort of thing, potentially.
Great, thank you. I think there was a.
I was just thinking the same question. From my point of view, you could still, based on the interaction, construct the knowledge graph. You just possibly try to do some like sort of loopings and trying to confirm some consistency. So it doesn't have to be a representation. It could be a symbolic graph.
It could, yeah, that would be interesting to see how you would actually like ensure consistency based on, so you'd have to make sure that like the next graph that you generate is sort of factually consistent with everything that you've done previously through your entire history of actions.
Yeah, exactly.
Yeah.
So based on this interaction, you have this partial graph, and then for the next one, you're trying to build on top of the existing graph. Trying to figure out if there's contradiction, then you sort of backtrack.
Yeah, I mean, I think that's definitely a very open problem, at least in the NLP world, of like ensuring like factual consistency out of large transformers kinds of models. Yeah, it's definitely, I think people are making progress, but like even the sort of latest and greatest things, like, you see like ChatGPT and whatnot, are still really prone to just like making stuff up. Yeah.
This is pretty deterministic. All the actions are predefined. Everything is combinatorial.
It's combinatorial, but there's a decent bit of stochasticity in the environment itself. So there might not be as much agent side stochasticity, but in the environment there's stochasticity, because like it's like, other characters move around in different ways. objects move around. Yeah, so there's environment side stochasticity that's like not as, that's a little bit difficult to like ensure consistency with. Yeah.
Because from my point of view, it felt like the word environment could be reconstructed as the typical knowledge graph in NLP, right? Everything is deterministic. But if you
Yeah.
have some moving parts, then probably potentially you have to make that stochastic in certain
Parts of the graph. Yeah. So like the way we're sort of handling that is like, you've seen a thing. So like you were in a room previously, right? And you saw a snapshot of the room. So what this is, the knowledge graph is like less of a deterministic thing, and it's more of your belief state on what you think is happening in that room right now. And until you go back to the room and actually like observe it again, that's what you think it's like, or that's what you think it's most likely to be like, when in reality, like things could have changed, right? There's like characters that could have like walked into that, like, you know, people that could have walked into the room that weren't there previously. You know, there's, you know, they could have moved around objects.
So the
Yeah.
graph's not globally shareable across different games.
Yes, they're not globally shareable, basically. Yeah, you would have to sort of, it's built sort of like, it's episodic belief states is, I think, the sort of right way of thinking of this.
Yeah, I feel believe there's commonality among the graphs that potentially construct.
Yes, that's the idea, is like, if you can find, you know, what are the kinds of like these sort of subset of like facts that are held across all of these, a bunch of these, then you can use that as the sort of common sense information to go from world to world. As you know, you don't have to start training RL from scratch every single time. It's like, what is the common sources of information that you have? And yes, like that is the holy grail. Yeah.
Is that what common sense is? Is this shared?
It's,
Can you like
yes.
Can you say that's your definition of common
That's my definition of common sense. Whether the other people at AI2 agree with me is a different, but it's the sort of like shared like axioms of the world that you learn through interaction, basically widely applicable. No, I don't see anything in chat.
Yeah, Zunzun doesn't have any question, but I have one more question.
Oh, yes,
I-
please.
one question. So, actually, I want to hear your thoughts about your work in the context of all this like GPT-3 or ChatGPT, right? So you show an example that it doesn't really work perfectly for your case, but it gets really close, right? It's like it almost understands the task. So if you redo the work now, will you think about different approach? Like, or like, is there a way that you can leverage that power?
Yeah, that's a really good question. So, the other sort of half of my work is almost entirely reinforcement learning from human feedback. And so what I'm thinking of, and like what we're working on currently, is basically like merging those two things, and is basically doing human feedback that's sort of grounded in the dynamics of the environment. And so even in the sort of GPT-3, the chat GPT kinds of like cases, right? I think like what's really happening is there's just like, they basically have, it's really just a data problem, more or less. Like they have full-time annotators that are sort of just like sitting there and like writing out and so if it's the case that, you know, somebody wrote out how to build a circuit through this sort of feedback mechanism, then I think it could do it. Absolutely. But if it's like a novel task, right, like it sort of breaks in these kinds of cases. If you say, you know, give me how to test if an aluminum foil is conductive, I don't think it can give you sort of a procedure like you would see on like WikiHow, but then that's still not really like executing it in the world. So there's sort of multiple levels of this, right? So there's like, if you have a question, is aluminum foil conductive? That's super easy to answer. We've solved that already. Then there's the question of like, how to test if aluminum foil is conductive, which I think like we're making some amount of progress towards right now. And then there's the sort of future question is like, given an arbitrary material, like then how do you like sort of test conductivity for that? And I think that third one is something that I've actually tested on like ChatGPT last night, actually. And it still like doesn't. It basically gives you the same answer that I showed you on the screen. It's like, just take it, put it like, on the ends. And so if you're like, how do I test if a bar of plutonium is electrically conductive, right? Like you probably would want an answer that says like, please don't touch the bar of plutonium. Except this says, bring the bar of plutonium into your lab and, stick it to two ends of a battery. So I think it's definitely a feedback problem. And, given sort of like theoretically enough feedback, you could basically solve this. But what if there's cases where you don't have human feedback, right? Like you can't get human feedback for everything. And so I think you really need agents that can learn from this sort of environmental feedback by just like testing things out themselves.
Yeah, I totally agree. I feel like the part that's really missing with all the large models
is interaction.
Even interaction and feedback that
Yeah.
can actually improve.
Exactly. Yeah. So I think they've done a really like OpenAI has done a really good job at basically getting to learning once from non-noise. So like they have very specific mechanical Turk, like not even mechanical Turk, it's like a full-time annotators. We've been doing a lot of like mechanical Turk kind of stuff, and it like doesn't work nearly as well because if they're not very highly trained annotators, the feedback is too noisy to actually get anything useful out of it. But that's why we need to sort of like actually like go towards like learning from noisy user feedback, learning from observation that's like grounding within an environment. Yeah, I think that's yeah.
You mentioned earlier on that you were interested in applying these agents to environments with things like visual input. Could you elaborate a little bit more on like what kind of game worlds and inputs you're considering and what kind of ideas you're pursuing?
Yeah, absolutely. So the most immediate project that we're doing that's a follow-up of this is in Minecraft. And so I don't know if you're familiar with there's something called the Mind Dojo environment. And so so some of their authors and I are basically working on this idea of given the sort of like high level like textual like description of a particular task, have a world model that sort of like decides to split that like large task up into smaller subtasks as natural language strings. Whereas, I mean, there's been a couple papers that have been doing different versions of this, but, split the smaller subtasks in a way that can actually be like, grounded in the environment. So it's like constrained to the dynamics of the environment. So it's like, go shear a sheep requires you to find some shears, find a sheep, go like actually go up to the sheep and like, clip the sheep. Right. So that's the exact sort of like follow up. And again, like in that case, also like the agent is using like graph-based representations for a state to then try, instead of in this case, predicting the next state, it's trying to predict what its next sub goal is going to be in natural language form based on the current state.
As a follow-up, I know just from my knowledge of like that Minecraft environment that to get for the sheep shear example, to actually create the shears, there's like a very complicated like crafting process.
Yeah, exactly.
That involves many different steps before that process is completed. Do you plan on modeling that kind of crafting, sort of all the steps that you can take in the world, the sort of representation of the world that you're building, or you plan on sort of giving that information to the model just as a baseline?
So I think where we're at, it actually works. So if you give them that information to the model, so like if you're like, okay, so it's almost like language conditioned options, if you're familiar with options at all. So it's like, oh, so make some shears, and you can just sort of have like options that give you the exact sort of right sequence of actions to do that. Actually works really well. Except like that's not particularly realistic, right? Like of just giving it that sort of pre-baked information. And so now we're looking at like, sort of discovering these kinds of, reusable submodules as like, build shears, and like, this is the sequence of action that you use to build shears. And it's like, okay, can you reuse that again next time you hear the language string, build some shears? And so, yeah, that's sort of how we're looking at it now, is like actually try and figure these out step by step. Oh.
Let's see how does this work. I think the audio is on.
Maybe you could type this question as well in the chat box. We're over time anyway.
Yeah, I don't see anything in chat. I'm happy to like take